In this video, you will learn about direct variation. So to understand what direct variation is, let's use an example. Now here, this is a table showing the number of hours that you work and the amount of pay that you earn. So for example, you work 1 hour and you get paid $12. You work for 2 hours and you get paid $24. You work for 3 hours, you get paid $36. 4 hours is 48, 5 hours is 60. So here, H, this first column, is the number of hours, and P, the second column, is the amount that the person is paid. Now we can represent this table with an equation. Notice the relationship between the number of hours and the pay. What I'm doing is I'm taking the hours and multiplying by 12. Right? 1 times 12 is 12, 2 times 12 is 24, 3 times 12 is 36, and etc. So the pay is equal to 12 times the number of hours that the person works. So 12 times H for hours. So my equation is P equals 12 times H, or more simply written, P equals 12H. Okay, so this is an equation I can use to represent the table. And notice that if the number of hours double, the pay also doubles. So if I go from 1 hour to 2 hours, the hours double, and so does the pay. 12 times 2 gives me 24. Right, if I go from 2 to 4, 2 hours, 4 hours, my pay goes from $24 to $48. So if the number of hours double, then the pay doubles. If the hours triple, the pay triples, etc. So because of this, because as the hours increase, the pay increases, we say that the pay varies directly as the number of hours worked. Okay, the pay varies directly, or we can say the pay is directly proportional to the number of hours worked. So this example is considered a direct variation because both the hours and the pay are increasing. As the hours increase, the pay increases. This number 12 right here, the 12 that is being multiplied to show the pattern, so like from hours to pay, 1 to 12 or 2 to 24. This number 12 that compares the two is called the constant of variation. And it's a constant because it's a number that does not change. Each time I'm multiplying by 12. 1 times 12, 2 times 12, etc. So it's called a constant because it's not changing and it's showing the relationship between the hours and the pay. So here's a definition of direct variation. Our definition says that x and y form a direct variation if the ratio y over x is always equal to a constant k, where k is a positive number. Meaning if I take this right column and divide it by this left column, it will always equal the same number. So here we see 12 and 1. If I take 12 divided by 1, that's going to be 12. 24 divided by 2 is 12. 36 divided by 3 is 12. 48 divided by 4 is 12. And 60 divided by 5 is 12. So that is my definition. And our description of this is going to be as one value increases, the other value also increases. And as one value decreases, the other value also decreases. So here we saw the number of hours. As those increased, your pay also increased. If your hours decreased, then your pay would also decrease. So here are a couple examples where you're to determine if this table represents a direct variation or not. So what we need to do is see, is there a relationship or a pattern with the x column and the y column? So for example, the x column multiplied by 6 would give me the y value for the first number. So like 1 times 6 would give me 6, right? Check that for the other ones. Is that pattern true? Well, 2 times 6 would be 12. We know that. 1.5 times 6 would equal 9. Alright, so because we're multiplying by the same thing each time, yes, this would be a direct variation. And if you wanted to write this with an equation, we can write this as y equals 6 times x, because we took 6 times x to get y. And the constant of variation would be the number 6, because that is what we're multiplying by each time. Alright, and if you did not see that we were multiplying by 6, what I can do is I can take the y value and divide by the x value. So for example, 6 divided by 1 would give me 6. I take the 9, divide by 1.5, that would also give me 6. And then 12 divided by 2 would give me 6 as well. Alright, so if you did not see that the pattern was multiplying by 6, I can go through that pattern by dividing y by x. And this number 6 would be your constant of variation. Another example, if you had this table where you have 16 and 12, 24, 18, and 30, 24. Alright, so here we can try to determine if there is a pattern that holds true for each set of numbers. So here we take the 12 and divide by 16 to see what we get. We can reduce and we get 3 over 4. So what that means is we're taking 16 times 3 over 4 to get 12. Okay, now check the next set of numbers. We have 24 and 18. Well, if we take the 18 divided by 24, we're going to get that to reduce by dividing top and bottom by 6, which would give me 3 over 4 as well. The next set of numbers, we have 24 and 30. If I take 24 divided by 30, I can divide the top and the bottom by 6, and that would give me 4 over 5. So because not all of these are the same, we have 3/4, 3/4, and 4/5. Because 4/5 is not the same as the other two, this would not be a direct variation. Alright, so they all need to be the same number, same pattern, in order for this to be a direct variation. Here is another example. We have 2, 5, 4, 10, and 6 and 15. So what I do is I check each set of numbers and see if the pattern holds true between each set. So I do 5 divided by 2. Alright, then I do 10 divided by 4, which can reduce to give me 5 over 2. And then do 15 divided by 6, divide top and bottom by 3, which would also give me 5 over 2. So yes, this would be a direct variation. If I wanted my equation, this 5 over 2 is what I'm multiplying by to get from 2 to 5, or from 4 to 10, or from 6 to 15. So like 2 times 5 over 2 is 2, 4 times 5 over 2 is 10, 6 times 5 over 2 is 15. So the pattern, or the equation, is we take s, the s column, and multiply by 5 over 2 to equal t. So that's my equation. T equals 5 over 2 times s. And the constant of variation would be this 5 over 2. Alright, so that is my constant. Here is one more example with a table. And here we have fractions. Alright, so the question is, do we have a direct variation? And if so, what is the equation and what is the constant of variation? So to determine this, alright, we could do d column divided by the t column. So like 1/4 divided by 1/2. That's one way to do it. Or you can just kind of look at this one and see that if we take the t column and multiply by 1/2, that would give me the d column. Right, because 1/2 times 1/2 is 1/4. 8 times 1/2 is 4. 14 over 3 times 1/2. 1/2 of 14 is 7, so 1/2 of 14 over 3 is 7 over 3. So the constant is 1 over 2 because I'm multiplying by 1 over 2 each time. Alright, so this is a direct variation. So yes, it's a direct variation. The constant is 1 over 2, and my equation is I take t and multiply by 1/2 to get d. Alright, so I can write this as t times 1/2, or d equals 1/2 times t. Same thing. Alright, so that is how you work with tables. Now, if you were just given an equation like this, and you were told to determine if this is a direct variation or not, what we need to look for is this first term right here, this 1/2, the coefficient needs to be positive. So it needs to be positive, and notice there's nothing being added or subtracted to this expression. And if you look back in the video at the other examples, there was nothing being added or subtracted. It was simply multiply by something. Alright, so let's look at the next slide, and we'll take a look at a few different examples of equations, and we will determine if we have a direct variation or not. So equation number 1, we have y equals 2 times x. Is this a direct variation? Well, yes, because this 2 is positive, so 2 would be your constant, as positive, and there's nothing being added or subtracted. So this would be a direct variation. Here we have y equals 2x minus 3. This is not a direct variation because of this negative 3. What about r equals 4 times t? Well, yes, because this coefficient is positive, and that would be your constant. The constant is 4. Now what if you had y equals negative 2x? This would not be a direct variation because this number in the front is a negative number. Alright, it needs to be a positive number for it to be a direct variation. So at this point, we have learned how to recognize a direct variation, and how to determine the constant of variation, and how to write as an equation. Now at this point, we now need to transition and be able to work with direct variations to solve different problems that we come across. So to do this, we need to know how to convert from English into math notation, and then use that to solve an unknown. So let's begin by working with translating from English into math notation. Let's say we were told in English that some value y varies directly as x. Okay, y and x can be anything. It could be representing, the pay in the hours, or it could be representing the amount of time that you run and the calories burned, or whatever. So x and y are representing two random values. And another way we can represent this in English is we can say that y is directly proportional to x. So the phrase varies directly and directly proportional mean the same thing. Now, if you were given this statement in English, you can convert this into math notation by having this set up as y equals k times x. So we take the y and then equals k times what? It's k times x right here. To make this more clear, let us think about the problem that we showed in the previous slide with the hours and the pay. We said that the pay is directly proportional to the hours, right? As the hours increased, the pay also increased. So pay was our letter P, and hours was H. So we could have said P is directly proportional to H instead of with pay and hours. So the P and H are just representing pay and hours. Same thing here. Y and X are just representing two different things. Could be pay and hours or whatever. Okay, so our equation, as we showed in the previous slide, was P equals, and there was a number there, and that was the number 12. Okay, because 12 was our constant, right? That's what we multiplied to get from the hours to the pay. So it's 12 times h. Okay? So same thing with our setup for anything. It's going to be y equals k, some number, some constant, times x, times your other value. And here the k is called your constant. So it's called a constant, or also called a constant of variation, or constant of proportionality. Okay, so it can be called any of these things. Now here's an example. If you were told to convert z varies directly as h into math notation, how you'd write this is z equals k, our constant, times h, times this value. So make sure you know how to convert from English into math notation. Another example, m varies directly as a. So this would be m equals k times the letter a. And that's my equation. We have another term called jointly proportional. So what jointly proportional means is a quantity varies directly as the product of two or more other quantities. So it means directly proportional, but instead of directly proportional to one value, it is directly proportional to two or more values. So here's an example illustrating that. If you were told z varies jointly as f and c, this is a directly proportional problem. So the setup would be the same as before. So it would be z equals k times, and it's going to be times f and c. So k times f times c. So multiply by both f and c instead of just the one letter like we did before. Example 4, if we said z varies jointly as x and the square of y. So again, we can write this as z equals k times something, and it's going to be k times x and times y squared, the square of y. So my equation would look like this. So now that we know how to convert from English into math notation, we need to now know how to work with this. So how to use these equations to solve different problems. So for example, if we said that s is directly proportional to t, and s equals 20 when t equals 15, find t when s is 64. So what I have here are two different scenarios. S is 20 when t is 15. So we're going to use this scenario 1 to figure out our constant, figure out what is the relationship between these two values. Okay, and once we find that, we're going to use that information, use that constant to solve for scenario 2, where it says find t when s is 64. So to begin this, I need to convert this statement into math notation. S is directly proportional to t. So that written in math notation would be s equals k times t. And what I do is I use scenario 1, so I use the 20 and 15, I plug it in for s and for t, and I can solve this for k. So s is 20 when t is 15. So I have 20 equals k times 15. So solve this for k. K times 15, I get rid of the 15 by doing the opposite, which is dividing. So I divide both sides by 15. So I have k equals 20 over 15, which can reduce by dividing the top and the bottom by 5. And that gives me k equals 4 over 3. So I know the constant, and that's what why I use scenario 1. So I use this to find the constant. Now from here, I can do the equation one more time for scenario 2, where I plug in what I know. So I know that s is 64, and I know that k is 4/3. This constant does not change from scenario to scenario, right? It's a constant. It's a number that does not change. So I plug a 64 in for S and a 4/3 in for K. So I have 64 equals 4/3 times T. And I can solve this by getting rid of the 4/3. So I'm trying to solve for T. So 4/3 times T, I do the opposite of multiplying, which is dividing. So I divide by 4/3, which is the same thing as multiplying by the reciprocal. So that's the same thing as multiplying by 3/4. So let's multiply both sides by 3/4, because that's the same thing as dividing by the 4/3. So on the right side, the 4/3 and the 3/4, when I multiply, will cancel out. That gives me 1/1, or just 1t. So I have t equals, and then 64 times 3/4. So I can multiply those together, and 64/1 is the same thing. The 64 divides with 4, and that's going to give me 16 and 1. So I have 16 times 3 on the top, and 1 times 1 on the bottom. So 16 times 3 would give me 48. So my solution, my final answer, is that t equals 48. And that's what I was trying to find. I was trying to find t. Here's another example. Here we are told that a varies directly as b, and a equals 50 when b equals 40. Find a when b is equal to 12. So here we want to use this statement to write a math equation. So convert this English into math. So we can write this as a equals k times b. And then we know that a is 50 when b is 40. So use this to figure out what is k. So this is scenario 1. So plug a 50 in for a, plug a 40 in for b. So we have 50 equals k times 40. So from here I can solve for k, and this is k times 40, so I get rid of the 40 by dividing. So the 40s will divide out. K would equal 50/40, which reduces to 5/4. So I have found the constant. So I'm not done yet, because my end goal is to find a. What I can do is I can use this equation again, a equals k times b. And I plug in k as 5/4, I plug in b as 12. So a equals 5/4 times 12. And then I solve this. 5/4 times 12, or times 12/1. 12 divided by 4 would give me 3/1. So I have 5 times 3, which would be 15. So my solution is a equals 15. I have 3 more examples I'm going to walk you through. And each of these examples has a little something different. So it's helpful to maybe continue to the end to pick up on some different unique scenarios you might come across. Here we are told that y is directly proportional to the square root of x. So the square root makes it a little bit different. And it says y is 30 when x is 9. Find x when y is 100. So what I want to do is take this initial statement and convert into math notation. So we can write this as y equals k times the square root of x. So that is my equation. Y equals k times the square root of x. And then I'm going to use scenario 1 to plug in and find k. So y is 30 when x is 9. So I plug 30 and 9 in for y and x. So 30 equals k times the square root of 9. So the square root of 9 is 3. So I have 30 equals 3 times k. Solve for k by dividing both sides by 3. So k equals 30/3, which would equal 10. So I'm not finished yet, but I can use this k to find x. So I now look at scenario 2. Find x when y is 100. I use the equation again. I plug 100 in for y and a 10 in for x. Or 10 in for k, sorry. So I have 100 equals 10 times the square root of x. So from here, I can solve for the square root of x by dividing both sides by 10. So we have the square root of x equals 100 over 10, which is 10. So I can think of this just logically here. The square root of what number is 10? So the square root of what gives me 10? That would be 100. Because the square root of 100 would equal 10. Another way I could have thought through that is I know I need to get rid of the square root, and I do the opposite of square root, which is squaring. So I can square both sides. If I square both sides, on this right side, the square and the square root will cancel out. Those are opposites or inverse operations. So I'm left with just an x left over, and then 10 squared on the other side, which would be 100. So either way, we get our answer of x equals 100. Example 8. This one uses actual information. So here it's not just letters. We actually have a real scenario. In this problem, it says the electrical resistance in ohms of a wire varies directly as its length. If a wire 100 centimeters long has a resistance of 10 ohms, what length of wire will have a resistance of 14 ohms? So to begin with, I need to look at the initial statement where it says the resistance varies directly as its length. Okay, so the resistance in ohms. Ohms is my symbol, varies directly as length. So we can use this symbol, ohms, varies directly, means equals k times something, and it varies directly as the length, so k times L. So here we see ohms equals k times L. So this is my equation, and from here I can plug in information from scenario 1, where it says a wire 100 centimeters long has a resistance of 10 ohms. So 100 is going to be the length, so 100 is L, and my ohms is 10. So plug a 10 in for the ohm symbol. So 10 equals k times, and then plug a 100 in for L. So 10 equals k times 100. I can solve this for k by getting rid of the 100 and do that by dividing. So divide both sides by 100. That will cancel. I have k equals 10 over 100, which would give me 1/10 or 0.1. Same thing. And you can keep it as a fraction or as a decimal, whichever is easier for you as you solve. So from here, we're not finished yet. We need to use this k, this constant, to determine what is the length of the wire that will have a resistance of 14 ohms. So I want to use this equation one more time. So ohms equals k times length. And I look at scenario 2. I know the resistance is 14 ohms, so plug a 14 in, and then k we said was 0.1. So we have 14 equals 0.1 times L. I can solve this for length by dividing both sides by 0.1. So that will divide out. I have 14 divided by 0.1. That equals L. And I can do this on a calculator, or I can multiply top and bottom by 10 to get rid of that decimal in the bottom. That gives me 140 over, move that over one space. So I have 140 over 1, which is 140. So my solution is that the length would equal 140 centimeters. Okay, one more example, and here we have z varying jointly as x and y. So this one is different because of the term jointly. So to begin with this one, we want to convert this initial statement into math notation. So in math, we would write this as z equals k times then x and y. So k times x times y. So that is my initial equation. And it says that z is 6 when x is 3 and y is 8. So we can use this scenario to determine what is k so that I can find z when x is 7 and y is 2. So plug a 6 in for z, a 3 in for x, and an 8 in for y. So I have 6 equals k times 3 times 8. Well, 3 times 8 is 24, and then I could divide both sides by 24. So k would equal 6 over 24, which would equal 1/4. So I found k, and now I know x is 7 when y is 2. So I can use my equation one more time and plug in that information. So 1/4 in for k, 7 in for x, 2 in for y, and I can multiply these together to find z. So what I have is 1/4 times 7 times 2, or 7 times 2 over 1. That's going to be 14 on the top and 4 on the bottom, which can reduce by dividing top and bottom by 2. That gives me 7 over 2, which would equal 3.5. So that is my solution for z. And that concludes our lesson for today. We will see you next time.